Hello, I hope you are doing well. I am doing great. Thanks for asking. So, today we'll be talking about quadratic equations. I remember some time back in campus, back in the good old days, we had a unit on numerical analysis and we touched a bit on quadratic equations. Obviously, it wasn't the first time coming across quadratic equations, they go back all the way to high school. But I specifically remember this period in campus because I was learning R and I remember trying to implement a solution or a function to solve quadratic equations in R, and either I couldn't figure it out or I was just lazy, but I ended up using the solution provided by R. There's a function to solve polynomials in R, so that is the one that I ended up using. So today I woke up and I was just chilling. Then I thought, you know what? I'll implement that solution myself. So here we are. And of course, the implementation itself is just like probably 5 minutes. I don't know. But I am going to take you through my thought process of how I arrived at that implementation. Okay, so let's get started. A quadratic equation, the standard form of a quadratic equation is ax squared plus bx plus c equals to 0. So this is the standard form of a quadratic equation. A quadratic equation has two solutions, right? And to get those two solutions, we can use the quadratic formula. So in this case, when you use the quadratic formula, you will say that x is equals to, then on the right hand side, it's a long equation. On the bottom, or rather the denominator, is 2a. Then for the numerator, you're going to have negative b plus or minus. Then we have the square root of b squared minus 4ac. So this is the quadratic formula. Let me label these. So we have said that this is the standard form. And then we have said that this is the quadratic formula. Okay, so now our focus, well, obviously this is the formula that you are going to use to solve the quadratic equations. Like, this is the formula that you are going to be implementing. But I'd like to take a minute and talk about this value of b squared minus 4ac, the one we are finding the square root for. So we want to talk about b squared minus 4ac. So this one, mathematicians call it the discriminant. So this is the discriminant. And we are in the formula, in the quadratic formula, we are taking the square root of that discriminant. So I want you to consider three cases because these are going to be important in our implementation. So what are the cases? I want you to consider a case where b squared, oops, let me change back to this color. I want you to consider a case where b squared minus 4ac is greater than 0, and then a case where b squared minus 4ac is equals to 0, and finally another case where b squared minus 4ac is less than 0, because those determine whether the quadratic equation has real solutions or imaginary solutions. Now tell me, you obviously know that we are looking for the square root of that discriminant in the formula, right? So tell me what happens when b squared minus 4ac is greater than 0. In that case, we are going to have the square root of a non-negative number. So probably the square root of something like 25, the square root of 50, the square root of 100, etc, etc. Point is, it is a non-negative number. So when b squared minus 4ac is greater than 0, what we are going to get, in this case, we are going to say this implies that roots are real. The two roots of the quadratic equation are real roots. We are together up to that point. Now, next, let's consider what happens when b squared minus 4ac is equals to 0. In fact, before we talk about that, let's talk about this last one. It's probably, I have something to say about the middle one. So let's talk about the last one. The last one for b, the case when b squared minus 4ac is less than 0. What happens in that case? When b squared minus 4ac is less than 0, we are going to be looking for the square root of a negative number, right? So this means we'll probably be looking for the square root of negative 25, negative 50, negative 100. But obviously, the square root of a negative number is not real. It's imaginary. So we are going to have such a situation. For example, you're looking for the square root of negative 25. So obviously, this doesn't exist, but we know that the square root of negative 25 is the same as doing the square root of 25 and then multiplied by the square root of negative 1. So we know what the square root of 25 is. It's either plus or minus 5. And then the square root of negative 1 doesn't exist, but we say that is imaginary. So we call that I. So this becomes I. So the final answer for this becomes plus or minus 5i. So that is the answer for the square root of negative 25. So we must keep in mind that when implementing a solution, when this discriminant b squared minus 4ac is less than 0, it will mean that the roots are going to be imaginary. So here we say roots are imaginary. Okay, now let's talk about the middle case. It's actually my favorite. When b squared minus 4ac is 0. When the discriminant is 0, that means we are looking for the square root of 0. So it means that the two roots are going to be equal, because if this whole part of b squared minus 4ac, if all this evaluates to 0, it means that x can only be negative b out of 2a. In that case, we say that the two roots of the quadratic equation are identical, right? I mean, yeah, because x is just negative b out of 2a, so the two roots are going to be similar. So for that, we scroll down a bit and we are going to say when b squared minus 4ac is equals to 0, this implies that the two roots are, one, they are real, definitely, right? So they are real, but they are also identical. So the two roots are real and identical. So we are together up to that point. Something else to note about this b squared minus 4ac is that this right here, because that we have said that the two roots are real and identical. This is the case for perfect squares in quadratic equations, right? Now, what are perfect squares? Let me just write here. We are talking about perfect squares. You get a perfect square when you multiply a number by itself or an expression by itself. So when I tell you to take 3 and then multiply that by itself, you get 9, and we say that 9 is a perfect square. When you take something else, another number like 5, you multiply it by itself, you're going to get 25, and we say 25 is a perfect square. So this can be anything. So long as you're multiplying by itself, then you get a perfect square. The same happens for expressions. So when you take an expression like x, then you multiply it by itself, you're going to get x squared. X squared is a perfect square. Even when you take something like xy and you multiply this by itself, you're going to get x squared, y squared, and we say x squared, y squared is a perfect square because you got it by multiplying by multiplying an expression by itself. Now, let's talk about the case of quadratic equations. If I give you the roots of a quadratic equation, we have already said that a quadratic equation has two roots, right? So assume that the two roots are going to be alpha and beta. So alpha is the first root and then beta is the second root. This could have been any other variable, it's just a placeholder. So let's assume that the roots of a quadratic equation are alpha and beta. How do you get the quadratic equation? You come and say x, then you minus the first root, alpha, and then you multiply that by x minus the second root, which is beta, and you equate this to 0, right? So that is how you get a quadratic equation when you are given the roots. But what happens when the roots are identical? So when alpha is equals to beta, then what happens? So it means that in that case, to construct the quadratic equation, you're going to say x minus the first root alpha, then times x minus the second root, which is still alpha. And we say this is equals to 0. So let's expand this. So we are going to take this x, we multiply it by this x. We take this same x, multiply it by negative alpha, and then we are going to take this negative alpha, multiply by this x, and take that same negative alpha, multiply it by negative alpha. So let's go. So x by x, that's going to give us x squared. Then x by negative alpha will give us negative alpha x. Then negative alpha by x, sorry, negative alpha by x will give us negative alpha x. And finally, negative alpha by negative alpha will give us positive alpha squared. And we're equating all this to 0. So let's simplify this. This becomes x squared, and then negative alpha x minus alpha x will be negative 2 alpha x, and then plus alpha squared, and we are saying this is equals to 0. Now, remember, I told you that the standard form of a quadratic equation is ax squared plus bx plus c. And by this point, it's pretty clear that to solve it, we need to be able to identify the value of a, the value of b, and the value of c. So let's come back here. Tell me, what is the value of a? In this equation, the value of a is 1, since that is the coefficient of x squared. So this is the value of a. And then what is the value of b? The value of b is always the coefficient of x. So the value of b is going to be negative 2 alpha. And then finally, what is the value of c? The value of c is going to be alpha squared, positive alpha squared. Now, with that, what I want you to notice about perfect squares for quadratic equations is that b squared is always equals to 4ac. And to prove it, since we've already expanded this, now we can say what is the value of b squared. B squared is going to be, we take our value of b, which is negative 2 alpha, and then we are squaring that. So what does this become? This is negative 2 alpha multiplied by negative 2 alpha, and this is going to give us negative 2 by negative 2 will give us positive 4, and then alpha by alpha will give us alpha squared. Let's talk about the 4ac. If we want to calculate 4ac, we are going to do 4 times the value of a. The value of a is 1, right? And then multiplied by the value of c. The value of c is positive alpha squared. So that becomes alpha squared. And what does this give us? So we take 4 times 1, that's still 4 times alpha squared becomes 4 alpha squared. And now you see the two of these are identical. They are equal, right? So for perfect squares in quadratic equations, b squared is always equals to 4ac. It also means that this equation, if we take the 4ac to the left, it will mean that b squared minus 4ac is equals to 0. And that is what I was talking about where? Here. So when b squared minus 4ac is equals to 0, just know that the two roots are identical and that we are talking about perfect squares. And moreover, in that case, for perfect squares, or rather when the two roots are identical, the solution for the quadratic equation is always going to be negative b over 2a. So for this one, well, actually, you don't need to write it. We just know that the solution, when it's a perfect square, we are going to always have negative b out of 2a. Yeah, so I think I've talked enough about this. Now it's time for the implementation. So let me just switch things here a bit. Okay, so let's switch to the terminal and start the implementation. So here we are, and for our quadratic function, it's going to be, well, we are going to call it solve quadratic. I couldn't come up with a better name. Uh, and then it's going to be a function which takes the values a, b, and c, just as we have seen from the quadratic formula. We need the values a, b, and c. And the function is going to be returning a list of a named list of three values. The first one, as you can see in this example, is going to be alpha, the first solution for x. Then we have beta, the second solution. And then I prefer returning, this is optional, but I want my function to return a type. So tell me, are the roots that you have given me real or imaginary? Yeah, so that's basically it. So let's start the implementation. And then actually, I do have some tests here. I think they are like 4. Yeah, just to avoid manual testing. But for these two cases on this file, we are just going to do manual testing. After they pass, we're just going to run the tests. Let's get started with this implementation. So obviously, we have said that the first thing we need to calculate is the discriminant, because it is going to determine how we solve the rest of or rather how we go through, how we go about the rest of the solution. So let's start with the discriminant. And we have said the discriminant is always b squared minus 4 times a times c. That is the value of the discriminant, b squared minus 4ac. Then, now tell me what happens. Let's start with the case for perfect squares. I think that's much better. So we are saying if the discriminant is equals to 0, that is for perfect squares. So if the discriminant is equals to 0, what do? Let's calculate the solution. So I'm just going to call it alpha. Yeah, let's just go with alpha. So we know that the two roots are identical and they are given by negative b over 2a. So this is going to be negative b over 2 times a. And that's it, right? Then we said we want our function to return a list. The first value is going to be alpha, and that's just alpha. And then I want you to return beta. In this case, alpha and beta are identical. So we say alpha, we say beta is equals to alpha. And finally, I want you to tell me the type of these values, the type of the roots. Are they imaginary or are they real? In this case, they are going to be real. Yeah, that's it. So this is what we want to return. So we can just assign it to out. And then we are going to say, sorry. We are going to say, I want you to return out. So that first case is done. Now let's talk about what if the discriminant is greater than 0. If the discriminant is greater than 0, we know that we are going to get 2 real roots. So how do you go about that? In that case, we are going to say, we are going to calculate some value for alpha and then for beta. So for alpha, this is going to be negative b, and then let's go with plus, and we have to find the square root. So we are saying negative b plus the square root of the discriminant, and all of this is over 2 times a, 2a, right? Yeah, let's just go with, 2a. So 2 times a. So alpha becomes negative b plus the square root of the discriminant and all of that over 2a. And then for beta, it's going to be the same thing, only that the difference, we're not going to do negative b plus the square root of the discriminant. We are going to do negative b minus the square root of the discriminant, and the rest of the formula stays the same. And then now, what do you want to be given out? So alpha becomes alpha, beta becomes beta, and finally, the type is still real in this case, and we want an early return, so I want you to return out at that point. Now, if we have checked whether the discriminant is equals to 0, we have checked whether the discriminant is greater than 0. Now, there's only one remaining possibility. The discriminant is less than 0. So that means we are about to deal with imaginary numbers. So how do we handle that? What we need to do is deal with the square root portion, right? So we are going to say let's just call it the square root part. How are we going to handle it? We are going to take the absolute value of the discriminant. So the absolute value of the discriminant, and then we are going to multiply it by the square root of -1. And actually we are going to take, well, the square root the square root of the absolute value of the discriminant, and then we are going to multiply it by the square root of -1. And what is the square root of -1? That's going to be I. And luckily for us, R understands I. So we're just going to say times 1I. So R will handle that part for us. So that's going to be the square root part. So once we have the square root part done, we can now talk about what do you want to be alpha. So alpha is still going to be, we still do -b, and then we say plus the square root part, and then all of this is still over 2a over 2 times a. And for beta, it's the same thing, but now instead of -b plus the square root part, we do -b minus the square root part. Sorry. So that's alpha, that's beta. Then we can now have, what do we want to give out? We have alpha equals to alpha, beta equals to beta, and finally, now in this case, the type is going to be imaginary. And then of course, I want you to return out. So the function isn't, it could be shorter, but we should first test before we even start making it shorter. But this is it. This is the implementation for this function for solving quadratic equations. So what I want us to do is, since we have this first test case in quotes, it's not a test case, but since we have it, I want us to run and then see if we get an alpha of 1.5, a beta of 1, and type to be real. So let's fire up the terminal, and I'm just going to do R script and then that. And there we go. It looks like we in fact got it right. So let's see. Let's also try for the imaginary one, for the imaginary example. So let's fire up the terminal and then we run that. So R script quadratic equations, and so we get 3 plus 2i, 3 minus 2i, and the type is imaginary. Okay, yeah, we got it. Actually, the first time I implemented this, which is like, I think an hour ago, I didn't get it right. I'm getting it right because it's something I have already done. So don't get too excited. Anyway, so that's it about the tests. And actually, let's run some real tests here. So what I'm going to do, let's actually just fire up that terminal again, fire up R, and then I am going to source that quadratic equations.r file, and then I am going to run the test. So I'm just going to source tests, and all the tests are passing. So our function is correct. Okay, so now let's do some, it's too long for no good reason. The first thing I have noticed is that we keep on repeating this denominator. We have 2 times a, we have 2 times a again. We have it like, I don't know, 5 times. So that means we need to say denominator will be 2 times a. So in all these cases of 2 times a, we're just going to have the denominator, right? So instead of all these, we'll just have the denominator, 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 and there we go. And then something else I've noticed is we don't need to assign, we don't need, okay, maybe in this first case, we need to assign the alpha because we are using it for the beta here. But for the rest of the cases, we don't need the assignments. So let's get rid of those. So we just cut this and have it there. Then we do the same for this. We cut it and then we have it for the beta. So now we don't need all that. Okay, that's looking good. We do the same for this one. For this one, we cut the value of alpha and we paste it there. Then we do the same for the value of beta, then we paste it there. So now we don't need these 2 lines. And then we don't need this last assignment here since it's the last value. And sorry, since R is a functional language, the last value is returned as the return value. So we just cut and there we go. Okay, now this looks good to me. Yeah, it looks good to me. So let me rerun the test to ensure I didn't mess something up. So I'm going to source quadratic equations.r, then I'm going to source the test. And there we go. I didn't mess anything. So this is the implementation. And yeah, I'm pretty satisfied. Yeah, as always, thanks a lot for watching the video and have a great day.